So, my name is Marco Squarcina. I'm a PhD student at Ca' Foscari University. And this is a joint work with my colleagues, Mauro Tempesta and Francesco Palmarini, here in the room, and also with Riccardo Focardi and Graham Steele. So the title of this talk is Mind Your Keys, a security evaluation of Java keystores. We start with some background and motivations behind our work. So, key management is considered, generally speaking, one of the most difficult tasks in cryptography. And part of key management is key storage. So how you securely store your keys. If you have an hardware facility, you can use smart cards, or if you are part of a large organization, probably you are used to use HSMs, which are basically large and expensive servers storing in a safe way keys and providing an interface like a PKCS11 to interact with keys, to use keys without exposing them in the clear. Otherwise, there exist software solutions called keystores. And the keystore is basically just a file containing some cryptographic keys secured and certificates secured by a password. Ideally, we'd like a keystore to provide some properties like confidentiality. So you don't want keys to be leaked to untrusted parties. And you want also to identify if the keystore file has been tampered with by an attacker, so key integrity. And also by dealing with the keystore, so by loading the keystore, you don't want that your system is armed in any way, of course. I said protected by a password. What does it mean? Of course, it means providing some kind of crypto on top of from a password. And to do so, we use a KDF. So a KDF is a key derivation function used to derive a cryptographic key out of a password. And a KDF function accepts some parameters. These parameters are, of course, the password, and then a pseudo-random function like SHA-1, a salt, random salt, and an iteration count. The iteration count states how many times the SHA-1 function is applied within the KDF. Okay? And as a result, you obtain the cryptographic key. Salt is used to avoid precomputation because you put a random string inside it, and the iteration count is used to slow down the attacker because the cost of computing the KDF is expensive, because I said here 10,000 times. So imagine performing 10,000 of times a SHA-1 function. Okay. So motivation about behind our work. I told you about KDF, but when we started looking at keystores, we didn't know what kind of cryptographic mechanisms were used within each implementation. The only thing we knew was that there exist 7 different keystore implementations in the Java ecosystem provided by Oracle JDK and the Bouncy Castle cryptographic library. And we also knew that the keystores are used by leading applications like Tomcat, WebSphere, and Android Studio. So just an example, in Android Studio, the key used to sign your applications is stored within a JCEKS keystore. Okay, so we thought it was important to expose flows found within each implementation and to study these keystores, right? So yeah, we found some concrete attacks and some flows, and I'm going to talk about them right now. First thing is about the JCEKS password cracking. So let me use the light saber. Okay, so this scheme here is how JCEKS decrypt a cryptographic key. Okay, so you can see here E is the cryptographic key in encrypted form, and at the bottom here there is the cryptographic key decrypted. So it's the plain text of the key, and it works like this. So you take the salt at the beginning of each cryptographic entry, and then you concatenate the salt to the password. You do the SHA-1 out of that, and you obtain the first block, first 20 bytes of the key stream. And then you take this result, you concatenate it again to the password, and you do the SHA-1 again, and you obtain the second block, and you go on like this. So you obtain a key stream W here, and by XORing this key stream with the encrypted key, you obtain the plaintext key. This is, I mean, really, really weird and flawed as a cryptographic scheme because there is no KDF, and it's really just a matter of performing like 100 more or less SHA-1 operations. But then we thought, if we are an attacker, can we do something better to rule out a password to mount a brute force attack against this kind of cryptographic scheme? And then yes, it is possible because we exploited the knowledge of the binary format used to store the plaintext key to, I mean, just recover those bytes out of the first decryption block and rule out most of the password with just one SHA-1 operation. So this attack has been implemented in Hashcat, a well-known brute force tool, and with just one single GPU, it was possible to perform 8 billion of attempts in 1 single second. So it should be, I mean, quite clear that this kind of keystore, which is up to Java 8 included, the default keystore used in Java, you can't achieve key confidentiality with this kind of keystore and with this kind of implementation. So, still talking about JCEKS and JCEKS, this is how integrity is enforced. And there is a SHA-1 hash at the end, attached at the end of the keystore content. And it's a SHA-1 of what? It's the SHA-1 of the integrity password here of the string Mighty Aphrodite. I mean, that string, Mighty Aphrodite, and the keystore content. So in this way, if an attacker tampers with the keystore content without knowing the password, it is not possible to recompute a valid SHA-1, and then the user can understand if the keystore has been tampered with or not. What is the problem of this scheme? Well, again, it's really weak because it's just about performing one single SHA-1 operation to ensure to test one password. So there is no KDF, and there are no iteration count and no salt. And indeed, since there is no random salting, it is also possible under certain cases to mount a rainbow table attack, so to increase the efficiency of the key recovery attack, of the password recovery attack, sorry. Moreover, theoretically at least, it is possible to add more keys, more data at the end of the keystore content and recompute a valid hash without knowing the password here by doing a length extension attack. Okay? So we also asked ourselves, why did they use Mighty Aphrodite as a string? So we Googled for Mighty Aphrodite, and we figured out that in '95, the year in which JDK, the first beta of JDK has been released, there was a movie by Woody Allen called Mighty Aphrodite. So this is probably, I mean, some developers probably are some fan of Woody Allen. So, okay, another problem is loss by integrity parameter. And this is how it is supposed to be. So this is the correct way of enforcing integrity over a keystore. So you pair a KDF and an HMAC, and HMAC is not vulnerable to length extension attacks. But what is the problem here? The problem is that the parameters of the KDF are stored within the file, and you need to read those parameters to perform the KDF that then computes the key fed into the HMAC. So an attacker, by tampering with these parameters, can DOS the application by setting an insanely high value to the iteration count. So you can just hang the application by setting billions of iterations performed to the random function. Okay, so now let's move to something really, really shocking for us. At least when we figured that out, it was really shocking. And yeah, so JCEKS also supports for storing symmetric keys. And symmetric keys are stored as secret key objects that are serialized and encrypted within a sealed object, which is, again, serialized inside an entry of the keystore. So at this point, when you load the keystore, the routine, loading the keystore file, deserialize each sealed object, and when the parsing of all the entries is done, well, the integrity check is performed. So we thought, instead of serializing a sealed object, what about serializing a malicious payload? Because we gave a look at the code and we found that there were no checks at the deserialized routine. So basically, you can put whatever you want there, which is not even checked by the integrity function, okay? And by doing so, you can rely on a well-known technique when you deserialize unsafe content. And using a code reuse technique, basically, you can even achieve code execution. And we did that on outdated versions of the JDK. On more modern versions of the JDK, we found that it was possible to perform a DOS by putting the application on an infinite loop. And this problem here has been fixed in the October critical patch update by Oracle developers. So you think it's enough? It's not enough, of course, because there is an additional deserialized call. And yeah, indeed, here you have another deserialized call of the secret key object, which is encrypted this time. And we placed our malicious payload inside the sealed object. This is even better than the previous case, because you can access from this place here, since you are using a different deserialized routine, the one provided by the sealed object, you can access a wider class path. And you can also use code gadgets found within third-party libraries, such as Apache Common Collections, for example. And by doing so, we were able, if you know the integrity password and the password to achieve confidentiality of that key, to obtain common execution even on the latest JDK. Okay? This is not yet fixed, so we are basically dropping a 0-day right now. So yeah, we suggested to rebrand JCEKS from Java Cryptographic Extension Keystore to Java Code Execution Keystore, because this is really what it's doing. So, okay, the timeline about our disclosure and the contributions of our work. We discovered, well, we started with this analysis the last year, and we found the code execution during a hiking competition in Russia in April. And instead of drinking vodka and enjoying our nights outside, our PhD life was about working all day and night. And yeah, we went on with research and found this vulnerability. So we reported next month the vulnerabilities to Oracle and Bouncy Castle. And it has been fixed. I mean, most of the problems have been fixed in the Oracle CPU of October. And they issued a couple of CVE for us. And yeah, then we gave a look at the code again, the JDK, the new JDK released by Oracle, and we found that the code execution problem has been just partially fixed. So the second deserialized exploit is still something, still nowadays. So, okay, apart from that problem that they didn't fix correctly, and it's supposed to be fixed in the next CPU, which is scheduled for April, I guess. We were really proud of our work because we managed to push developers to increase the security of all the keystore implementations out there. And yeah, so Oracle now modified the key tool, which is the standard tool to access keystores. And now if you are loading a JKS or a JCEKS keystore, it states a warning saying that the keystore uses a proprietary format. So you should move immediately to a more updated keystore format, and the standard one, which is PKCS12. That is also the standard keystore if you're using Java 9. And the number of iterations has been drastically improved from 20 to 200,000 iterations for JCEKS, with a ceiling value of 5 million to mitigate the problem of DOS parameter abuse. And same thing for PKCS 12 and for many other implementations provided by Bouncy Castle. So, of course, due to time constraints, it was not possible to tell you all the bits found in the paper, but also we provided a threat model for password-protected keystores, and we also distilled some design rules for the development of a secure keystore. As I said, we analyzed in depth 7 different keystore implementations. We exposed for the first time the cryptographic scheme underlying these implementations and found concrete attacks and weaknesses. Also in the paper, you can find a comparison of the brute force time for all the analyzed keystores, so it will be really easy to understand what is the most resistant keystore out there, both for confidentiality and for integrity. And for me, it was a pleasure to do this project because for the first time, it was really possible to push the security of concrete cryptographic libraries. And that's all. Thank you very much for your attention. And if you have any questions, I'm here.
Any questions from the audience? Well, I have a question to start with. Have you thought about generalizing your research to other types of keystores other than Java?
Yeah, this is, of course, a future work. I mean, yeah, due to time constraints, we only analyze the keystores implementations found in Java and in Bouncy Castle, I mean, in Oracle, JDK, and in Bouncy Castle. But yeah, of course, we plan to move to other implementations and give a look there, because probably there will be more interesting things to discover.
And that may be another paper.
Yeah, exactly.
Okay. Other questions from the audience? Okay. If no other questions, let's thank the speaker again.